So sampling and quantization are the two aspects of data acquisition systems. Okay, so there are two parts to this. One is quantization. So this is basically transformation of digital signals, sorry, my bad, analog signals to discrete states, so discrete outputs. And the second step is coding. That is ultimately everything we talk about in digital theory is zeros and ones. So we need to assign the outputs to digital code. Okay, so I'll talk about both these aspects now. So for this, we have what are known as analog to digital converters, A/T. Okay, so analog data, typically sensor data, for example, is analog, some value between, say, 0 and 5 volts. The output, however, has to be for the microcontroller for Arduino, it needs to be processed as some digital value with zeros and ones. Okay, how do you do that? Okay, now typically when you buy or look at analog A to D converters, you have 8-bit, 10-bit, 12-bit, and so on. Okay, so what it means is that this basically defines the resolution of the analog to digital converter. So the resolution is 2 raised to n, where n is the bits of A/T converter. Okay, so let's get to that in a bit. So if you have sample three-bit A/T, now you don't really buy a 3-bit. That's like 30, 40 years back, you could buy a 3-bit. Now you don't really have 3-bit because you can have much more powerful A to D converters. But let's say that you did have a 3-bit A to D converter. That means that it has 2 raised to 3 equals to 8 levels. And that also is a measure of the resolution. Resolution of the A to D converter. So what do we do with the resolution? So let's say an example where we use the resolution in order to encode some sensor value. Okay. So the example is as follows. Okay, so let's say that the input voltage is in the range of 0 to 4 volts. And how can we use a 3-bit A/D converter to store these, or converter to I guess, interpret or analyze the input voltage. Okay, so if you imagine there's a sensor, the sensor can output something between 0 and 4, and that means something with respect to the physical quantity I'm measuring. It could be intensity of light, it could be distance, so on. That's not important. What is important is that we want to take the 0 to 4 and convert that to a signal which the computer or microcontroller can understand with a 3-bit A to D converter. So what will happen in this case is we will essentially identify the number of levels we have, which will be 2 raised to n, n would be 3, so we have 8 levels. That means we can store the numbers from 0 to 4 as 8 levels. So one way to do this is we break this voltage into bins, 8 bins. So let's say 0 to 0.5, 0.5 to 1, 1 to 1.5, 1.5 to 2, 2 to 2.5, 2.5 to 3, 3 to 3.5, and 3.5 to 4. So 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now we'll assign each of them to a state. So we'll call that 1, we'll call this 2, call this 3, call this 4, call this 5, call this 6, call this 7, and call this 8. Well, rather I should, 8 is fine. So 8 levels. We have 8 here, the state, and this was totally intentional. Why I went with 0.5 was because I can then break it down into 8 levels. That's why. And then we'll create a general formula for this. So now what we'll do is we'll create a code, and that code is going to be a binary code. So the binary code is, well, we want to have all numbers till 2 raised to n minus 1, so 7. So the code for this one would be 0, 0, 0. That's the number 0. This would be 0, 0, 1, 0, 0, 2, sorry, my bad, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Right, so I'm just converting the numbers 0 through 7 using the code. Okay. Okay, so now if the input voltage from the sensor was, I don't know, 3.2 volts. So if it's 3.2 volts, then we'll see that it belongs in this range, right? So we have 110. For this, the code is 110, and the microcontroller will save this as 110. Okay. So I talked about two things earlier. One is quantization, and then the code. So the quantization and coding. The quantization was the first step. This is quantization. Okay, once we did the quantization, remember the quantization was done because of the number of bits in the A to D converter. And then this was the coding part. Okay, so this way we were able to bin the entire range and then use an A to D converter to store it. So if you asked me 110, what is, so 3.2 converted to 110, but if you ask me what is 110, then the A to D converter would either say 3 or 3.5. It depends on how you code it. Either you code it with the least least value in the range or highest value in the range. Clearly, this is not ideal because when you converted that 110 back to the number 3 or 3.5, you lose the 0.2 volts. It's gone. So clearly, a 3-bit A to D converter is not able to efficiently, not efficiently, but accurately map the range from 0 to 4 volts. So clearly, you need more number of bits or a higher range A to D converter. So this gets us to what is known as the resolution of the quantization size of the A to D converter. The quantization size is basically the maximum voltage minus the minimum voltage divided by 2 raised to n. So in this case, the quantization was 4. So here we had 4 minus 0 divided by 2 raised to 3, which is 8, and that was 0.5. And that's what you saw over here. These ranges were 0.5 apart, right? I got this from that formula, and then I went about doing all this math. So there is so this means is that you can only measure or you can only store values in the range which are 0.5 volts apart. Anything which is less than 0.5 volts cannot be stored with this A to D converter. And that is there's a problem with the resolution. It's a problem with the number of bits available. So a 3-bit A to D converter is not very good to store values. So what you want to do is you want to go for an 8-bit or a 10-bit. So if you have a 10-bit, so if you choose a 10-bit using a 10-bit, what we'll have is 4 minus 0 divided by 10. So 2 raised to 10. Calculate that. .004 approximately. So you can measure and save values which are 0.00, which change by a value of 0.004, which is highly accurate, just with 10 bits. Okay, now, if to give you a context with this, if you remember, maybe 4 or 5 years back, we had a 32-bit operating system. So now you cannot buy a 32-bit operating system. It's only a 64-bit. So that has 2 raised to 64 levels. You can think the amount of levels available, which means that how much you can, with what resolution you can store these values. So when you talk about programming in C, you have long double floats. If you remember, float can go only, I think, to something like 65,000, but a double can go almost twice that, and that's because of your because of this resolution. It gives you an ability to store bigger and bigger numbers in your computing unit because of the bits. Okay, so this is 10-bit is very limited. And we have gone far away from that.